Yeah, I'm recording now. But like the design aspect should be pretty cool. Quick course overview. So there's two parts to this course. We've got they can't hear me. We've got concrete materials, so that's looking at cement, minerals, admixtures, aggregates, all that kind of stuff. Pretty much what concrete's made of and the properties of that and how it's made, pretty much, right? So if you guys watched the concrete lecture this week, you guys would have gone over the kilns. Well, I actually don't know myself, I'll be honest. But there's also the water and aggregate stuff, right? That's the one thing I know. So topic 1 and 2 you guys should have covered already. And then topic 3 is fresh and hardened concrete. So yeah, I'm not sure what's in that either, I'll be honest. But they do talk about mineral admixtures, curing concrete, all that kind of stuff, right? And it also touches on some of the properties of hardened concrete. So like compressive strength, which is the most important one. So characteristic compressive strength after 28 days. That's what we use in the industry to actually determine the compressive strength that we need to use. All right. Second part of the course is reinforced concrete design. Right. So there's actually quite a lot of topics to it. So there's introduction to reinforced concrete. That's pretty much looking at the mechanical properties of concrete. It's building on from ENG2400. So you guys would have seen in ENG2400, they in week 5, you guys covered the beam stuff and like with steel bars going through it. You guys might have seen that. And then you guys might have seen T-beams as well. Some stuff like that. We're pretty much going to be building on that. Just in that first topic. It's really short. It's pretty easy as well. Topic 5, flexure. Flexure is pretty much looking at our bending moment capacity for our concrete member or concrete slab, right? So it's pure calculations, right? You're gonna be calculating the capacity of a certain beam and comparing what's actually acting on it. I'll cover that in a bit more detail. So I've actually got a bit of notes on it later on. So I'm gonna cover in a bit more detail. Flexure, shear. You guys know what shear is, hopefully. Like, it looks something like that. It's shearing at that spot there. We're also going to be taking a look at the shear capacity of concrete. Serviceability is a bit of a weird one. It's completely new. You guys have probably never heard. Oh, actually, you guys might have covered it in ENG2400 very briefly. Deflections. So serviceability is related to deflections. So in this topic, we're pretty much just going to be looking at how much the beam deflects, how much our slab deflects, and comparing that to the maximum limit provided to us in the standards. Excuse me. Have you guys heard of the AS3600, by the way? Concrete standards? No? What's up, mate? Takes a year late. No one's heard of AS3600? How about in the back? Have you guys heard of AS3600?
Yes, we have.
What is it?
It's a concrete standard.
True, correct. So what the concrete standards pretty much is, it's something provided to us as like a design guide, right? So if we're, let's say, designing for flexure, for example, we're designing to resist bending moments. There's actually a guide and step-by-step recipe on how to design for it, right? Certain requirements that we have to follow, certain things that we have to be careful of. It's all listed in the standards, and I've actually got it open here as well. So this is how that goes. So this is the concrete standards. AS3600 2018 is the one that we use. There is one coming out this year, but for this course, you guys are going to be using 2018, I think. So here it is: design procedures, properties of materials, design for durability. What we're going to be looking at in this course: design of beams, strength and serviceability. Slabs, it covers 1 week. All right, we're going to take a look at slabs. Columns, you guys look at in week 10. And literally nothing else. So the standard itself is like huge, right? and unfortunately the AS3600, it's a bit of a shit standard. Whoever's watching, don't quote me on the below. It's like it's a bit confusing. Alright, there's something else called the commentary. So there's two parts to it. There's like the actual standard themselves and commentary provided to us by the people who made it, I think. Right, but it kind of explains each of the equations. It just explains the standards. In this course, you don't really need to print out the whole standards, right? It's not like Steele's. The Steele standard is very, very good compared to this. And plus, you're not even allowed to bring it. So you guys have a closed book exam, right? Yeah. 1-page cheat sheet, double-sided, right? But you can't even like. You're gonna have to like fit everything into that double-sided cheat sheet, right? Which is actually doable. I'll show you guys mine in a bit, but yeah. So for example, let's take a look at the standards. At the very start, we have all of these symbols, definitions for our symbols. So for example, let's take a look at, just past it. Let's take a look at F-C. F-C, right? This one here. So that's the characteristic compressive strength of concrete at 28 days, where he uses this value a lot throughout this course, right? Most of the standards is pretty much built upon this, or what we look at in this course is built upon this value. Then if I flip to like a certain chapter, let's say I go to, no, I don't like this chapter. I don't like this one either. Alright, let's look at this. So this is like crack control, which you guys don't cover in this course, covered in later courses. Randall, that's so funny. Crack control. But yeah, so there's, as you can see here, depending on our bar diameter and our maximum width, crack width, what our maximum steel stress is. Right? So it's like looking at the values, comparing them and trying to type shit, right? Anyways. So that's serviceability. That's not serviceability, but that's the standards. Serviceability is, as I said, you're comparing your deflections to a certain limit. There's also detailing that's covered in this course. So that's talking about steel detailing. So, for example, I'll just quickly pull up a quick example. So you might have a thing like this. Let's say you have steel bar. According to the standard, for the mark to get one, you have to add like this hook at the end, right? That's not how it is, but that's covered in that topic, which you guys, it's not assessed, right? Excuse me, are you a student here? Then we take a look at one-way slabs, right? It's pretty much a combination of everything that we've done, but instead of it being one singular beam, we're going to be taking a look at a slab, right? And then you look at the design of columns, right? Okay, cool. Anyways, any questions so far? I'll probably rank these in difficulty real quick. Shoot. I'd say flexure is pretty hard to understand. One-way slabs is pretty hard. Shear is pretty alright. Serviceability gets 2 stars. This is easy and this is easy. So overall, it's a pretty difficult course. Not really. If you guys lock in, you guys will be fine. Trust me. Alright, anyways. Now, in terms of continuing with the course overview, I want to cover the second half a bit more in detail first, and then move on to the first half. So, in structural engineering, right, we've got something called the strength limit state design, right? So this is like a fundamental equation that we have that all the structural engineers use to design a certain structure, right? So does anyone know what this actually means? You guys might have seen it in geotech or steels. Does anyone know what it means? Wow. Not fair enough. But pretty much, there's 2 sides to this equation, right? The left-hand side we've got our reduction factor and our design capacity. And on the right hand side, we've got our actions, all right? So let me explain this with an example. So take a look here, we've got a beam, and on that beam, we've got some sort of load acting on it. That's not too hard to understand, right? We've got a beam with a load acting on it. Cool. So, this left-hand side of the equation, what it's talking about is the capacity of the beam itself. So we're taking a look at the capacity of the beam. So I'll highlight this in green. The right-hand side of the equation is talking about the forces that are acting on the beam itself. Right? So the equation is saying the capacity of the beam has to be greater than what's acting on the beam. Does that make sense? So imagine you have a beam, and there's some sort of load acting on it. If the load is greater than what it can handle, it's gonna what? It's gonna fail. Right? It's gonna snap. Right? So it's a pretty simple equation. Think about it. Like, if I break it down, it can't take more than what it can handle. Right? Tough? Crunch? Yeah, tough. Anyways, this RD part, that's based from the standards, right? So there's like a whole procedure to actually figure out what RD is. Reduction factor, does anyone know why we apply a reduction factor? So a reduction factor varies from 0 to 1, somewhere in between there. Why do we apply a reduction factor? Any ideas? People who did steels? Yeah? Safety? Yeah, safety in a sense. So pretty much what we're doing is we're kind of forcing the capacity to be lower than what it actually is. So we're kind of under-exaggerating in a sense, right? That makes it, if you think about it, a bit more safer. So let's say I'm looking at this phone, right? The actual capacity might be like, let's say 100 newtons, right? But I'm going to take it as 600 newtons, right? So whatever I'm designing, so it can actually take, I can like be more sure that it can take more than what it can handle. Right? I'll come back to that because the next part is going to be the factored action. All right, so there's actually these load combos that we need to use. I'm sure you guys might have seen it if you did steels. We use these load combos to figure out what our action is. So what we do is we kind of exaggerate our actions. We kind of make it seem more than what it actually is. Right? So in combination with the reduction factor, so I'm saying the load acting on it is like higher, but what it can handle is lower. Right? Excuse me? No, I'm just kidding. Anyways, what essentially that means, essentially, is we're designing it to take more of a load. Does that make sense?
So it's like a big safety factor because you're directly applying more load while it can take more load, but then what's it good? What you're saying you can only take like less than that.
Exactly. Yeah. So
it's like a bigger gap.
yeah, essentially, yeah. Yeah, perfect. Anyone not understand that? Alright, cool. No one said anything? I'm gonna move on. Essentially, to find our factored action here, we're actually given some combinations in the standards. So there's two kind of loads. There's something called a dead load, there's something called a live load. There's also some others like earthquake load, wind load. Those aren't covered in the course. The only thing we care about in this course is a live load and a dead load. So dead load, that includes self-weight, anything hanging from the ceiling. So let's take a look at the floor, right? The self-weight of the floor plus anything hanging from it, we call it a superimposed dead load, right? That is all a part of dead load, right? Live load is like shit that's moving around, right? Like you might have a person walking, you might have like chairs moving, tables moving, people coming in and out. That counts as live load, right? It exerts a certain force on like the structure, right? But it's like moving. It's not always constant. So we have two different kinds of combinations that we use, and any ideas should we take? So we have to calculate both of them. We have to calculate 1.2g plus 1.5q and also 1.35g. Do we take the maximum or minimum out of these two? What do we, maximum? Yeah. Why? Yeah, it's a worst case, exactly. So it's going to be, we're saying that there's more load acting on it, right? So this is a screenshot straight from the standards, AS 1170.0, clause 4.2.2. So we're taking a look at these two up here. Oh, by the way, this little d here, that stands for like design, right? So we're saying design capacity, essentially, right? Something funny? Random? Something funny? Okay, good. Yeah, okay, so I've kind of explained what this means. Sac. So that's pretty much like the overarching theme of structural engineering, right? We're taking a look at the design capacity of our structure and what's acting on it. And my iPad just froze. Sorry. Okay, now delving a bit deep into the kind of loads we can get, right? So we've got different kinds of pressures, distributed loads, which you guys have seen in Eng 1300, 2400, and also point loads or concentrated loads, right? So what I've done, each of these, I split them into two. So we've got G standing for dead load, right? Q standing for live load, right? So pressures are in kPa. So imagine you have a plate with like pressure acting on it, right? Yeah, that's what it looks like. And what we're going to have to do from there is use our load combos to figure out the governing action, right? Distributed loads are a bit more easier. I don't think we'll see pressures in this course that much. I don't think so. I haven't seen a question with it. But it's mainly going to be distributed loads and concentrated loads, right? So, yeah, they were saying the question, there's a dead load of WG is equal to blah, 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 WQ is equal to blah, blah, blah. Right? So I've actually put an example here of how to calculate your governing action, right? What to take for your factored action, essentially. If you take a look, so on this beam, simply supported beam, we've got a dead load of 2.5 kilonewtons per meter and a live load of 3 kilonewtons per meter, right? So they're both acting at the same time. Now I have to use the combination factors to figure out which one's governing. So I first calculate 1.35G, and I end up getting a load of 3.375 kilonewtons per meter.
So what do you mean by what's
Governing meaning we take the maximum. Yeah? So I'll show you what I mean. If I calculate 1.2G and 1.5Q together, it's going to be a higher load, right? So we're going to take the maximum out of those two. So I'm going to take 7.5 kilonewtons per meter as the load, as the distributed load acting on this beam. So we're pretty much combining the dead load, live load into one and making it into one UDL instead of two separate UDLs, right? And we call that W star, right? Make sense? So now, when I'm doing my calculations, let's say I'm trying to find the moment. I'm going to say this load is going to be 7.5 kilonewtons per meter. And then to find the moment here, maximum moment, W star L squared on 8, I use this W star value. Okay. Question?
So W and W2?
Huh?
G and Q.
Oh, sorry, yeah, this is G and this is Q, sorry.
And is that like live and
Yeah, exactly, yeah.
And why is it like, so what's with the 1.35?
Yeah. So the purpose of that is to exaggerate our load.
Yeah.
Right? So,
But why is it like two separate ones? Like what?
oh, yeah. So in the standards, they've actually told us that the basic combination for the ultimate limit state, blah, blah, blah. So the first case is let's say there's only the permanent action or the dead action, dead load.
Yeah.
So we're considering a case where only dead load governs, right? Then we're going to consider when they're both acting together, right? And out of those two, we're going to take the maximum.
Okay, so one is just dead load, and then the other one is the applied load, and we're comparing which one results in a higher load.
Exactly.
Just take that first.
Yep.
Because the one with the higher case will support the one with the lower case.
Exactly. Yeah. So you can test both cases out, but the one with the higher case, like it just makes sense to take that one. All right. Yeah, lovely. So that's loads. Hello, mate. We got Sigma. Come on, sit down. Take a seat. So that's pretty much me explaining this side of the equation, right? The factored actions. Now I'm going to quickly explain the design capacity part, right? So flexure, I've kind of talked about it. It's talking about bending moments, right? Acting in the beam. Shear is just shear. Axial, we're looking at tension and compression. We don't really look at tension and compression that much in this course. It's only in the very final week we take a look at a bit of axial loads in columns, right? Yeah, I don't think anywhere else. So pretty much for flexure, we're going to be comparing our design capacity to the critical moment, the shear capacity to the critical shear. We're going to be comparing it to the shear envelope, which I'll explain in week 7. I can't do it now. And then the axial capacity versus the axial force acting. All right. And this phi value, as I explained earlier, it's your reduction factor. All right. And from the AS3600 table 2.2.2, depending on your stress resultant, you have different values for phi. So for bending, you usually have 0.85, compression 0.65, tension 0.85, shear, I don't know, and then there's some other cases. Any questions? I was going to explain these in a bit more detail here, but before that I want to explain what reinforced concrete actually is and why we actually put steel in the bars. Alright, what's the point? Alright. So first of all, what you'll see a lot in this course is something like this. So this is a cross section of your beam, right? So my beam looks like this, or from a side view looks like that, and you've got some steel running at the bottom usually. I'll explain where you need the steels, but this is pretty much, I guess, 3D view of it. Does anyone know why we put steel in the bar in the concrete? Random?
Is it to support the different type of pressure that concrete itself is because one direction the steel helps support it?
Yeah, essentially. So pretty much concrete is pretty strong in compression. However, in tension, it's pretty shit, right? It's going to crack quite a lot. So let's say for this beam here, I've got some sort of UDL acting at the top. If you think about the way it's going to bend like this. Something like that, you feel me? That's horrible, wait. That's even worse. Good enough, okay? So that's the way it's gonna bend. And from Eng 2400, you guys might remember, our top fibers up here are gonna be in compression, so they're sliding into each other. However, at the bottom, they're gonna be in tension. Right? So they're moving away from each other, right? And because concrete's pretty weak in tension, right, it tends to crack at the bottom here. Right? So to prove, because it's weak in tension, what we do is we put steel bars where there is tension acting in the beam, right? So because there's tension acting at the bottom here, we'll put some sort of tensile bar here. Right? Fuck. Yeah, somewhere down there. Make sense? So pretty much wherever there's tension, we're going to be putting some bars. So I'll ask you guys a quick question. Where should we put our bars for a case that looks like this? Any ideas where? So we've got a continuous beam with 3 supports and a UDO acting up here. So think about how it might bend and think about where we're going to need it. Anyone? Rash? At the bottom? So all the way down here?
Yeah, well, that's
Split in better ways. What do you mean split in better ways?
let's put it in the middle.
Oh, in the middle. So like right here? Oh, fuck. Fuck. So something like this.
Yeah.
How come?
Is that what it was? Like the example above?
Sorry? It would be like the example above, but 2.
Yeah.
Okay. Okay, true. It's sort of correct. Yeah, the conch. What the hell are you even talking about? Like you talking about like this?
Yeah.
Hell no.
Not that easy, a bit more
Like
a bit like
like this? Why do you think this?
because there's supporting the gray areas as well.
Mhm.
There's 2 rows, 3 rows. So supports will still help.
Alright, I'll give you guys a hint. You can start and stop your steel beam, your steel rods, your reinforcing bars. You can start and stop them.
It's not easy.
You can start and stop. It doesn't have to be one continuous.
Oh, okay.
Yeah. So you can put it in different areas if you want, depending on how it's bending.
But you always just put it straight or you can put it at an angle?
Usually straight. Usually. Like as I said earlier, there might be like some hooks or like some cogs and whatever, but don't worry about that. Randall, any idea? Hey. So like this? What am I doing? Wait, hold on. Chill. Something like this and something like this. Not bad. Anyone else?
Are you asking like how to arrange this?
Steel bars, yeah. Okay. So if you think about how it's bending, alright? So it's gonna bend like this, like that, sort of, because of the support. Well, if you guys know how to draw this BMD, the BMD itself would look like this. Don't worry about the end part. So essentially, this part here is in tension. This part here is in tension. How about this part here? Tension. Yeah. So down here is going to be in compression. So you don't really need a bar down here, but up here you'll need a bar because the way it deflects, it's going to deflect like this. I'll try my best to like. Fuck. Something like this. Something like that. Right? So up here, it's actually experiencing some tension. Right? The fibers at the top are actually wanting to split apart. Down here, the fibers are also wanting to split apart. Right? Randall, what's so funny, dude? So up here it's in compression, up here it's in compression. So you don't really need the bar up there, right? But where you do need it is just up here, really. And then you'll need a bar down here and a bar down here. Does that make sense? Wherever it's in tension or like, yeah, wherever it's in tension, you'll need a bar. So if I want to draw out the bar arrangement, it will look, maybe something like this. There's like some rules to it about like seeds. Something like that. Is that right, Henry? Is that right?
I don't know, sir.
Oh yeah, that's true. Sorry. Why am I asking a third year student?
Yeah,
Yeah, so that's pretty much what it will look like. Any questions about that? Jen, you seem a bit confused. Oh, it makes sense? I do. Anyone else? Any confusions? Aston, make sense? Yeah? On that side? Makes sense? Oh, okay, beautiful. Hey, let me ask you guys another one then. For a cantilever beam like this with a dead load, like a point load acting at the very end, where should I put my reinforcing bars? Why at the top? Perfect, yeah. So think about how it's going to bend. So it's going to bend like this. Shit. Fuck. Like that. So this top part's in tension, so you need a bar there. Good job, Randall. W. Anyone not understand? So you can't put it at the top, you can't put it at the bottom. You put it wherever you want. Right. Follow your heart, essentially. Cool. Any questions about that?
So you're saying that would be good.
Huh?
With that one you could put-
Oh no. You would want to put it at the top because it's in tension. But sorry, I might have confused you a bit. You guys are late. Oh, thank you. You forgive me. Sit down. Jared, can you close the door, please? Oh, Cindy, thank you.
At the bottom of the beam, it's in compression and evaporate.
Yeah, it's in compression. So because concrete, we put it where it's in tension, right? So because it's in compression, you don't really need the thing at the bottom.
You don't need the bottom one.
No. So you put it at the top.
But in the bottom part, you need the bottom on the top.
Yeah, we have it at the top here because this top 5, it's in tension at the top.
Yeah, it's.
Confusion?
Wait, you're saying that you put
At the top, it's in compression.
No, it's not.
It's like that.
No. That's the you think about the BMD. Think about how it actually like deflects. Right? Think about it.
Deflect like that.
It deflects like like that.
Yeah, like that.
Alright. So I draw the deflected shape. What am I doing? Like that. Alright, so this top part here is like it's like stretching out the top. Does that make sense? Wait, let me actually draw the whole thing. Like that. Okay, that's the best I can draw. But if you think about it, it might be a bit understandable. Let's flip it around. Alright, you see how down here it kind of represents what we have here? Yeah? So if you think about it, we'll need a bar here where it's in tension. Yeah? Alright, cool. Alright, cool. It's still recording. Alright, cool. So I'm gonna quickly. Any questions? Hey Jared, I've got a question for you. Alright. Let's say we have a cantilever beam like this with a point load acting here. Where would you have to place your steel reinforcing bars?
Sorry?
Where would you like preferably put your steel reinforcing bars? Where would you put it?
I would put it perpendicular to
Like perpendicular like into the page?
Oh, you talking about like I'm thinking
Top or bottom? Oh shit.
I would put it
No, fair enough. So pretty much, no, it will be on the top. No, but the reason for that is because you'd want to place your bars where the beam itself is in tension, right? No, if you think about how it deflects.
No, you're right, actually.
It deflects like that, so the top fibers are in tension. Alright, it's stretching apart. Cool. That's my boy. Yeah, I can't.
Then at the bottom of the beam, very in compression.
Yeah, it's in compression this whole way.
Yeah, so you wouldn't, like, you know how we have, like, for the beam above, there was like two at the bottom and one at the top. Wouldn't we have like, mostly at the top and then at the bottom when it's in compression, and then put it at the bottom?
No, you only put it where it's in tension.
How do you put it where it's in compression?
Yeah. So the top's in tension. Yeah.
When you have one there when
It's in tension here.
and at the bottom
It's also in tension.
okay.
So it's in tension here, here, and here.
Makes sense.
Yeah. Okay. Beautiful. All right. Cool. I'm gonna quickly hop into Flexure. I'm not gonna go through it into detail. Just like a brief overview of it. So there's 3 stages when it comes to Flexure. We've got uncracked elastic stage. We've got cracked elastic stage, and we've also got we've got ultimate strength stage, non-linear. So pretty much it's fucked at this point, right? The beam itself. So at the top here, it's pretty much just N2400 calculations, right? It's exactly the same thing. I used the modular ratio method that you learnt, hopefully, and then there's something called the cracking moment. Henry, what's so funny, dude? So the cracking moment is pretty much the maximum moment it can take before it cracks, before the concrete cracks. Right? I'll delve into that in a couple of weeks, not now. One thing I want to cover about cracked elastic stages, once it does crack, it transitions into the cracked elastic stage, and the concrete at the bottom, so below our neutral axis, pretty much provides 0 strength, right? It provides 0 strength to our capacity. Anyways, this one, I just wanted to talk about this one because there's some things from the standards over here. Okay, I can't find it, but it's somewhere here, somewhere in the standards. Yeah. So, hello. So, the actual stress diagram looks pretty normal for the first stage. Second stage, it looks somewhat normal as well. Third stage, however, it becomes a parabolic. It becomes a parabola, right? So the people who made the AS3600s, they're just like, you know what, sack that. We don't want to work with that parabola. Let's make it into like a stress, like a block, a rectangle, right? And to convert it from a parabola to a rectangular stress block, that's what we call it, RSB. There's a few factors we're gonna have to calculate first and then multiply to F-C and DN. All right, I'll cover that later on, not right now. And then essentially to find the actual capacity, phi mu, you're gonna have to take moments about the neutral axis using our force diagram. Again, I'm gonna cover that later. Quickly, shear design, I have no notes on it. Shear design, there's a few aspects to it. The only thing I wanted to cover is the shear envelope. Hey, question? No? Yeah. I'm still, it's part of my app. I'm still covering like the overview, and then I'm gonna go through like the app in a bit. Cause like my app's meant to be like 1 hour, so like first hour I'll just spend on the course overview and stuff, and then second part I'll do the app. Yes. Okay, sack shear design. I don't want to go over it. Serviceability. So this is also from the standards. So this is a design table, the table full of our limits that we're going to have to calculate for. So pretty much the basis of serviceability is your beam or your structure, whatever, it's gonna deflect a certain amount. That's the thing. That's the deflection thing. It's usually this or this delta. I think it's called delta. And based off that, we're gonna have to compare it to what's given to us in the standards, right? And make sure that it's below the limit. So, actually, yeah, that's right. In this course, we only cover the total deflection. So for spans, it's going to be 1/250. So anything for like a simply supported beam or like a continuous beam, we're going to follow span over 250. So that's going to be our maximum limit for deflection. For a cantilever over here, it's actually 1/125. I've got that wrong, 1/125. 1/125. So pretty much you take span, the length of the member, divided by 125 or 250, that's going to be your maximum deflection limit. So for example, let's say L is like 4 meters. Our max limit is going to be 4,000 over 125, which is 32 millimeters. Okay? Does that make sense? Yeah? And then you're going to do like a bunch of calculations to figure out how much it actually deflects and then decide whether it's okay or not okay. Yeah? I'll show you like a quick... So these are all the calculations you're going to have to do. Yeah, it's pretty long. Anyways, the other thing I wanted to cover, the load combos I covered earlier, the 1.2 G plus 1.5 Q, 1.35 G. When it comes to deflections or serviceability, we're not going to be using those ones. So those ones are for strength, so for shear, flexure, and axial capacity, right? Yeah, that's what we call strength limit design. This is a bit different. We're looking at deflections now. So over here, we're going to be using short-term and long-term loads, service loads. All right, we've got WL and WS. So this is just going to be equal to G plus Q. Q. That's a Q, by the way. So these are going to be our new load combos, right? Psi. Yeah, I'm about to cover it. So this is from our table 4.1 in the AS 1170.0. So we're taking a look at these two columns. All right. Yeah, I actually don't know what the short-term, long-term factors actually mean. I just use them. But in all of our calculations, like when we're calculating, let's say, short-term deflection, we're going to be using WS, right? So I'll get into a bit more detail when I actually cover serviceability properly, not right now, because there's actually a lot to it. So I'm not going to cover it right now. But essentially, I just wanted to introduce you guys to long-term and short-term service loads. All right. Okay, so that's pretty much flexure, service, columns. I didn't really cover one-way slabs. One-way slabs is a bit of a weird one, right? So it covers like flexure, shear, and serviceability, but some of the factors that we use are a bit different. Right? Some of the formulas might be a little different as well, right? Henry, do you know if he's asked any one-way slabs question in the past? He has? Oh, okay, so he has. Okay, I was gonna say he hasn't, okay, but he has. So it's something you're gonna have to study for. Yeah. Okay, we'll take a break now before I start the actual yap. Alright. Alright, can you guys see? Oh. Should come on. It's not working.
How long do you think this will go?
Not, yeah, max an hour. Max an hour. What? It's not working anymore. Okay. Alright. Can you guys see? I can't really see you guys, so I'm gonna stand up a little bit. But okay, so we'll get started. So this is a continuation from the crash course. The second half of the crash course. So the first half I pretty much just went through the second half of the course, right? Like a course overview, stuff like that. And then, yo, what's up? Come on in. But then the second half, I wasn't too happy with how I covered it, so I decided to redo it now. And then, so I'm pretty much going to be covering topic 1, introduction to concrete and cement production and hydration, all that kind of stuff, right? Then next week I'll probably cover water aggregates and also fresh and hardened concrete. So to begin off, to start with, concrete. What is concrete? Yeah, so there's 3 parts to it. We've got cement, water, and aggregates. And we've got 2 kinds of aggregates. We've got coarse aggregate and fine aggregate, right? So cement and water, when we combine them together, we get a paste. That's why we call it paste. And then we have something else called mortar. Not from Clash of Clans, but we have mortar, which is cement plus water plus fine aggregate. Right. These are just like terms. You don't need to really like delve into it too much. It's not too important. But what I've got over here is straight from your lecture slides. The property relationships, weight and costs in a certain batch of concrete. You can see that in costs, cement is quite expensive compared to the rest. Right? Water is pretty much free, so you don't need to really account for it. But cement is a bit expensive, so that's why they actually add coarse aggregates, I'm pretty sure, because coarse aggregates, what it does is strengthens your concrete. Alright, so I've got it down here. Cement, like the uses for each of these. So cement, it acts as the binder, so it combines your gravel, your sand, your fine aggregates, coarse aggregates with the actual oh no, it just binds everything together. That's what it is. It acts as a binder, right? Like a medium. Water, it provides the medium for cement hydration. That's something we'll cover in a bit. So when water comes into contact with cement, right, there's a chemical reaction that undergoes called hydration, right? Fine aggregates, it fills the voids and improves workability, right? So it makes it a bit more easier to work with. Coarse aggregates, as I said earlier, it improves your strength for concrete. Now, any questions about concrete? Hella simple explanation for it, but there's really not much to it either. Right. Cement. So cement, it undergoes hydration when mixed with water to form a paste that binds our aggregates together. Fine aggregates and our coarse aggregates. Oh, by the way, I should probably add, fine aggregates, we usually use sand, and then coarse aggregates, gravel, right? Hopefully I don't have to explain too much into it. It's nothing too tricky to actually understand. So the most dominant cement that's actually used in Australia is called OPC, or Ordinary Portland Cement. Alright, wait, let me see if they can hear me. Hello? Oh yeah, they can hear me. Beautiful. So Ordinary Portland Cement, which is produced from 4 main raw materials. We've got limestone, clay, iron ore, and fly ash. So what I've done, I've drawn a few arrows to kind of indicate where these chemical oxides can come from, which raw materials they come from. So you can see that alumina comes from fly ash and also clay. Limestone only comes from lime. Iron comes from just clay. Silica comes from clay, iron ore, or fly ash. Alright? So there's a few things that I've also added here. We've got a chemical formula for our chemical oxides, and we've also got like a notation that we use in engineering, right? So instead of using the chemical formula, which is like, for us, it's a bit too complicated. You know, we're kind of stupid when it comes to chemistry. We use just C, F, S, and A. Right? Pretty simple to understand. And that's something you're gonna have to you're gonna try wrap your head around. Because later on, we're gonna be using, when we're talking about clinker, or we're talking about minerals, we're gonna be using the notation, the engineering note, not the chemical formula. And the way it's actually produced, so this is something I've taken from Henry's notes. This is like the production process. It begins with the raw material extraction, right? Quarrying raw material, pretty much going through the whole process of extracting everything out. And then, in a general sense, what happens next is grinding and blending, right? So you grind all of our raw material down, and you blend it with, I don't know, something. But after that, there's a process called pyroprocessing, right? So pyro means fire. So pyroprocessing just means it's getting heat blasted, essentially, right? It's going into it's going to get preheated, as I've said here, and then it goes into a rotary kiln, which I'm going to cover just in a bit. I'm going to talk about the thermal zones in a kiln just in a bit. After the pyroprocessing process, we've got the cooling process and the storage process. There's a note that I added onto the left here is we add gypsum and then we finish grinding. So gypsum, the reason we use it is because C3A, which is, I think, a clinker, but I forgot what it is. C3A, it's something that, it's a clinker, I'm pretty sure. It reacts instantly when water is added, which causes something called flash setting. That's something we actually want to avoid, right? So to counteract that, what we do is we add gypsum. Cool. This is like a whole lot of theory just all at once right now, but I'd say the production part, it's kind of good to have an understanding of it. I don't know if they will specifically test it though. They would test this thermal zones part, which I'll go through in just a bit. And then they would definitely test this stuff as well, chemical oxides and the clinker. Okay, so during that pyroprocessing step, right, the raw materials go into a kiln, a rotary kiln, however you say that word, and there are 5 different thermal zones. So this is covered actually pretty well in your lecture, but this is a simplified diagram that I took from Henry's notes, Zhang et al. Right here. But yeah, there at different temperatures, there's different thermal zones. So you've got 500 to 700, 500 to 950, blah 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 blah. What I've done here, I've told Claude to give me like a summary, like a brief summary about it for each zone, and the key reactions that take place. So in our first zone, the chemically bound water and the free moisture, so pretty much our evaporable water, non-evaporable water, similar to that, gets evaporated, and our clay minerals start to decompose. Our second part is calcination. So I've highlighted this equation is because it's actually a pretty important equation. At this point, I think this is where it actually starts to lose a bit of mass due to the carbon dioxide leaving. Is that right? I'm pretty sure that's right, yeah. Because the carbon dioxide gas is leaving during this zone, the overall sample just loses a bit of mass. So the free line begins to form B light, and calcium illuminates start to form. And I think there's a question about this in your workshops as well, like a chemistry question. So this is something they could ask in the finals as well. So that's why, this is something, that's why I've highlighted the equation. solid state reaction, the free CaO reacts with whatever that is, and that to produce B-light and calcium aluminates. And then after that, there's like when the clinkers actually form in that final zone. Yeah. So A-light, B-light. I've got a diagram down here somewhere. Oh, here. No, these are hydration. Clinker. What's clinker? Oh, I don't think I'm putting it in my notes. Well, are these are the clinkers, right? Oh, I should. Oh, here it is. It's right here. So we've got A-light that forms B-light, aluminites, and ferrites. So, in cement or in ordinary Portland cement (OPC), this is like the general composition of how much A-light, B-light, or how much clinker is in it. And those numbers, they don't add up to 100%, but they add up to 96.5. That's just wrong. 50 plus 25, 75. 75 plus 12 is 80 something. And then add another 3.5. And essentially the rest of it is like gypsum, water, some other things, right? Oh, maybe not water, but gypsum and some other minerals. I'm not too sure. But all I know is that these are the clinkers that are most important for you guys to know. Cool. Any questions? Beautiful. Now, cement hydration. So this is what I was talking about earlier. So cement hydration is the chemical reaction that takes place between cement and water, and it begins immediately when the cement comes into contact with water. It's also an exothermic reaction, which in this course doesn't really matter. It's just a fun fact, I guess. But there are two fundamental steps to hydration. The cement mineral, first what happens is it starts to dissolve. But there's actually a really good diagram from the lecture slides, which I forgot to include. But essentially it looks something like this. So that is our cement mineral, right? And then when water comes into contact with it, what will happen is it will start to dissolve, right? And then at a certain point, once it finishes dissolving, you get a hydration product that forms. Right? Hydration products being all of these down here. So I'll get up for a bit. So we've got our clinker, so silicates aluminates. This one down here I'm added from the lecture slides, but it doesn't get access, so you don't need to do it. Alright? We've got A-light, B-light, which they produce the same product, however, one is a faster reaction, one is a slower reaction. Okay? The CSHR contributes directly to the strength of concrete as well, which I've got over there. Now, for your illuminates, after you add a bit of gypsum, you get ethringite, which reacts with, which this is one of the products. However, if you have any residual CVA, your illuminate, they'll react from non-sulfur illuminate. There's a bit of a note that ethringite becomes unstable as the concentration of sulfur decreases. So I'm going to know that. But essentially, this is the fastest reaction, then followed by A-light and then B-light. I've actually got a note about this later on. But I think having this in a table helps a lot, or just having this in like a visual form helps a lot, something you can take into the exam. But yeah. Oh yeah, I've got it here. So in terms of kinetics, which is like your speed of your reactions, your C3A, your illuminates are the fastest, is the fastest. Then you've got C3S, which is, let me guess, alite. Okay, it is alite. And then you've got your C4AF, which you don't need to know. And then you've got your B light, which is your slowest reaction. So that actually brings us to this next point over here, stages of heat evolution. So the workshop has a really good question regarding this graph over here. It kind of goes through each of the stages and it explains it really, really well. Right? There's like one paragraph each for each stage that kind of goes through. Because of that, I'm not going to go through it. And it's not really that important either. Personally, you guys might find it important. I don't really care. Rapid heat evolution. So a key phenomenon is rapid dissolution of surface iron, whatever. This is what we care about, the practical significance. So the cement paste is fully workable. During the dormant period, pretty critical for concrete transport. The initial set occurs at the start, final set occurs at the end of the stage. So if we're taking a look at the accelerating stage, so your initial set begins here, and the final set final set at the end of the stage, so over here, which kind of makes sense. There's actually this kind of heat evolution graph for each clinker, so one for alite, B-lite, ferrite, whatever. And because C3S like takes up most of the cement, as we showed earlier, OPC, most of like this heat evolution graph, so this is just an overall heat evolution graph, but it will look very, very similar to our C3S one because it takes up most of the cement anyways. Yeah, this is kind of boring. Anyways, let's move on. Okay, a bit of math now. Degree of hydration, so, or DOH. DOH. Alright, so you got alpha, which stands for our degree of hydration. To calculate our degree of hydration, first of all, what is degree of hydration? It's pretty much how much cement has hydrated. Kind of self-explanatory, but it's the amount of reacted cement in grams divided by the amount of cement that we have. Another new term that I'm gonna introduce to you guys is called evaporable and non-evaporable water, which I've kind of explained down here. So evaporable water, you can kind of imagine in a sample like this, it's gonna have some voids. Right, it's gonna have some voids. Evaporable water is the water that fills these voids. Right, and what we can do is we can just oven dry it to get rid of that evaporable water. So it kind of evaporates water that can evaporate, essentially. Anyways, yeah. Free water in capillary pores, so in these pores or voids, whatever, it's water that just chills there. Its removal does not affect the hydration products. So if you remove that water or you keep the water, it doesn't matter, it doesn't affect your hydration products.
After it's queued.
No. This is like, actually, that's a good question. No, this isn't the concrete itself. I'm talking about just the cement itself, like the cement particle. No. So obviously you've got cement, but then to make concrete you need that cement. Right? So before we actually make that concrete itself, like we combine the cement, the water, and the aggregates all together. But just that cement itself, we're talking about one of those particles here. That's gonna have some voids as well. Then we've got non-evaporable water, which is a bit different. Its removal does not affect hydration products. Yeah, exactly. Okay. So this is chemically bound water. So this is water that is used to, I guess, form hydration products, right? So you're gonna need water, obviously, and we can kind of use the non-evaporable water as a direct measure of how much hydration has occurred. So the amount of non-evaporable water that we have in a sample kind of correlates to how much cement has reacted, in a sense, right? So there's this new formula for degree of hydration. It's the non-evaporable water gram per 1 gram of cement. So the amount of water in grams per gram of cement that you have, divided by the amount of non-evaporable water in a fully hydrated sample of cement, right? Which you've got these two symbols for. Sack that, it's not really that important. All you need to know is one of these two. Any questions about evaporable and non-evaporable water?
Okay, so what do you mean by per 1 gram of cement?
Sorry? Oh, so essentially,
Because after you added the water to it, so it doesn't
yes, yeah, exactly. Yeah. So like, the amount of non-evaporable water or the amount of reacted products per gram of cement that you have. Wait. Might need a bit of Henry's help. Henry, how do I explain this little part here? Like, it's the amount of non-evaporable water in grams per gram of cement.
I think it's because the thing at the bottom of the fraction, the non-evaporable water to hydrated cement,
Yeah.
that's like a known ratio.
Yeah. Oh.
Yeah, so you need to standardize the sample relative to the amount of cement you have. So yeah, it's I think at the bottom is like 0.23 is like the optimal fully hydrated cement amount. But that'll I guess like the amount of non-evaporable water you need. Can't just say you need 1 liter of water, you need 2 liters of water, because that doesn't apply in every case. You need 1 liter of water per however much cement you have. That's like a certain ratio. So for example, like say you want to make a dough, right, out of flour and water. It's like to get the perfect dough ratio, you need to add this much water per amount of flour. It's the same thing, it's a certain ratio. That's the thing at the top of the fraction, and the bottom of the fraction is like where the optimal ratio is.
Yeah.
It has to be standardized based on how much
Oh yeah, I've got something
flour
here.
you have.
To complete hydration, 1 gram of cement needs like 0.42 grams of water. That's like an optimal, I guess. Shouldn't it be 0.23? I don't know, I just took that straight from the lecture slides, but
I don't know. I actually didn't look at the exercise. I did the octopus from the workshop.
oh yeah, the workshop examples were really good. Yeah. Anyways, this bottom part is usually 0.23 unless stated otherwise. Does that make sense, Randy? What, non-evaporable water? Okay, cool. Alright, cool. Another important property I'm going to quickly talk about is the water to cement ratio. So it's actually one of the most important parameters when we're talking about the properties of concrete, right? So it's pretty much just a mass of water over the mass of cement, right? So it's just it's just mass of water over mass of cement. So if you have a low water to cement ratio, what we have is higher strength and durability. So it's a bit more stiff, it's a bit stronger, right? If you have something, but you don't want it too low, because if it's too low, what will happen is that it'll start to crumble, start to crack a bit more easily, right? There's like a sweet spot for it, right? But if you have too high of a water to cement ratio, sure, it's a bit more workable, right? It's easier to actually poor on sight, anything like that. However, the strength decreases, so you're kind of sacrificing the strength for workability. So typically we have it between 0.4 to 0.55. And in terms of content, that's pretty much all for topic 1. So that's how much I did last night. Next week I'll try to do the topic 2 and 3, water and aggregates, and the other one. But for now, I guess for the rest of this lesson, I'm gonna go through a couple questions. So question 7 of the workshop and a past paper question. Let's take a look at that. Any questions so far? Make sense a bit? I'm not too strong in this first couple weeks, so bear with me until week 3. I promise I'll do a bit better. But anyways, this is suck. Finals. So I'll kind of show you guys what you can expect from in the finals from these couple weeks of content. So they've given us a WC. This is actually for next week's. I'm not gonna cover that. This is also next week's. This is the past paper for 2021. This is also something for next week. Okay, lovely. So they don't even ask anything for week 1. What a useless week. They have something here. Here it is. So, for example, important mineral compositions are shown below. Estimate which of the 3 cements would have the highest strength at one day. What source of SO3 while producing? What is the source of SO3? And then what is the role of it? Did I cover that? Lol, I don't think I did. Anyways, what is SO3? Sulfite? Sulfur trioxide. Anyways, yeah, that's a question you can expect. This is another kind of question. After 2 days, actually from all of this, they don't actually tell us what the amount of evaporable water or non-evaporable water actually is, but you can actually figure it out after reading something like this. These are actually kind of hard, so I'm not going to go through it. I'm going to go through a workshop question instead, because I don't like these questions. I'm scared. Let's do one of Henry's questions. Question 7. Hey, this is a good one. You know what, in fact, I'm just gonna go. Actually, I'll let you guys give it a go. So, I'll kind of run through it really quickly. A paste was prepared using 45 grams of water and 100 grams of cement, and then sealed to prevent the loss of water. It was cured for 3 days and 7 days in constant room temperature. And after a specific curing period, the paste sample was taken and dried. So pretty much after it gets dried, as I said, that's when your non-evaporable water pisses off, right? Yeah, you don't have any non-evaporable water after it's oven dried. The samples were then moved to a muffled surface and then burned for 2 hours at that degree, that amount of temperature. Yeah, I don't know what that means. Yeah, I don't know what this means. Henry, what does 3 days and 7 days mean here? And was cured for 3 days and 7 days. Oh, is it 2 samples? Oh, it's 2 samples. Is it a solid by then? Is the question that Paris is asking. It's getting there. Yeah, definitely.
It's like how if you cure like a block of concrete, that will help the strength of the base.
Yeah.
But then it doesn't really matter how long it's cured for in terms of its strong properties. This is just the mass properties.
Gotcha. This is just mass properties, yeah. So, yeah, 3 days, 7 days. And then, yeah. So after it's moved to a muffled surface, that's when we're trying to get rid of that non-evaporable water. If that makes sense. So the difference in weight from from oven drying to original sample or mass after ignition, mass after oven dry, that's how you can find your non-evaporable water and evaporable water. So for example, this minus this is going to give you the amount of evaporable water in sample 1. This minus this is going to give you the amount of non-evaporable water. Does that make sense? Cool. And then please find the amount of evaporable water and also calculate the degree of hydration. Oh, so I've pretty much given you the first part of the question. So try the second part of the question. I'll give you guys like 5 minutes. Alright, cool. Continuing on real quick. I'll finish this off. So find the mass of cement in the samples. I showed you guys. Okay, whatever that means. Step 2, find the amount of evaporable water. So just minusing our samples. Non-evaporable water, as I said earlier, mass after ignition mass after oven dry minus mass after ignition. Yeah, you get that done. And then your degree of hydration is just, oh, what's our optimal? Wait, they've told us the optimal. Okay, they haven't told us, so we can just use 0.23, I'm pretty sure. Yeah, here it is. So for sample 1, our non-evaporable water ratio per gram of cement is 0.014, 104, sorry. And then for sample 2, 0.129, then you just divide by 0.23 and you get your answer. Any questions? They seem locked up. Any questions? Hey, I'll probably just end it there.
So what's the rest of the course like?